Hi class. In this lecture we continue our study of partial derivatives by moving into the concept of limits and continuity. So this is applying one of the first concepts that you've learned in your study of calculus of limits and continuity to functions of more than one variable. So let's introduce this concept by talking about the behavior of two functions that are both of two variables. So we have the function f, which is sine of x squared plus y squared divided by x squared plus y squared. And we have this other function g of x is equal to x squared minus y squared divided by x squared plus y squared. And what we want to do is we want to talk about what happens to the functions as both x and y approach 0. Okay, so what happens as the point xy approaches the origin? Well, first thing you're going to do, let's just plug in 0 for both x and y and see what we get. Well, if you do that, in both cases you get 0 divided by 0, right? You get the indeterminate form. Like sine of 0 is 0 divided by 0. This is 0 and this is 0. Okay? So when you have the indeterminate form, what that means is sometimes you can actually evaluate a limit when you have that indeterminate form. So let's talk about that here. So what we're going to do in this slide and the next slide is these tables here show the values of the functions f of x, y, and g of x, y, correct to 3 decimal places for points of x and y near the origin. So note that neither function is defined at the origin, right? Like you can't 0 to 0 is indeterminate form. It doesn't mean the function is defined. Well, look what happens here. Okay, this is the point of 0, 0 for x and y. These are corresponding points. Like this is the value of y is -1, x is -1. You get this for the function. Well, look what happens as x gets closer to 0. Okay, holding y constant at 0, you look like the value is approaching 1. Same deal. If you hold x equal to 0, and as y gets closer and closer to 0, it looks like this function, the value of y, is also going to 1. Okay, so it looks like what I'm saying here is the function here. It looks like this is going towards the value 1. Here's g of x, though. You notice that this is not the case. Okay, you're going to notice that the x values, as you get closer and closer to 0, looks like they're going to -1. Or excuse me, the y values, but it looks like the x values are going to 1 as you hold y constant at 0. All right, so it looks like this one, you have one going to 1, one going to -1. It just doesn't look like it's going to work out. Okay, so it appears that as x and y approach 0, 0, the values of f of x, y are approaching 1, which is what we see here, both approaching 1. And g of x, y aren't approaching any number. Like it looks like it's going towards one is going towards 1, and the other one is going towards -1. Okay, it turns out that these guesses based on numerical evidence are correct. All right, and we can actually write this is how we'll define the limit. So the limit as both x and y go to 0 of this function will end up existing and be equal to 1. Yet for our second function, the limit as x and y go to the ordered pair 0, 0 does not exist. All right, so in general, we're going to use this notation. The limit as x and y go to some values a and b of f of x, y is equal to some limit value L. Okay, so this indicates that the values of f of x approach the number L as the point x, y approaches the point a, b along the path that stays within the domain of our function. All right, so in other words, to make the values of x and y as close to L as we like by taking the point xy sufficiently close to the point AB but not equal to AB, a more precise definition follows. And this is just the delta epsilon formula or delta epsilon definition here. Basically, I'm not going to go through it, but the key concepts here is that we're looking at the limit as x and y goes to some values a and b, and if that limit exists, it's going to be equal to some real number L. All right, other notations you might see for limits are the following. You can see a limit as x goes to a, y goes to b, like this, instead of as an ordered pair. Or you could see it as f of x goes to L as x, y goes to a and b. All right. So for functions of a single variable, we let x approach a. There are only 2 possible directions to approach, left and right. Right. So when you're looking at functions of a single variable, for the limit to exist, the one-sided limits had to agree. So this is what you see here. When the one-sided limits for a function of a single variable are not equal, we say the limit does not exist. For functions of two variables, though, this situation is not as simple because we can let x and y approach a and b from an infinite number of directions. Okay, like you can come from this way, this way, this way, this way, this way, this way. It's really hard, okay? So the first definition we had says that the distance between f of x, y, and L can be made arbitrarily small by making the distance from x, y to a, b sufficiently small. This definition refers only to the distance between x, y, and a, b. It does not refer to the direction of approach. Therefore, if the limit exists, this function f of x, y must approach the same limit no matter how x and y approaches a and b. So from every single infinite direction for a limit to exist for a function of two variables, all the possible paths have to be pointing to the same value. Thus, we can find two different paths of approach along the function that has different limits, and if we can do that, then what we'll see is the limit does not exist. Okay, so what this is saying is if f of x goes to L1 as xy goes to AB along the path C1, but then f of xy goes to L2 as xy goes to AB along a different path C2, then we can say that since L1 does not equal L2, the limits do not exist. All right, let's show that this one doesn't exist and what I mean by these paths. Okay, so let's let f of x, y again be that function, x squared minus y squared divided by x squared plus y squared. So first, let's approach the point 0, 0 along the x-axis. Okay, so if you're along the x-axis, okay, that's the path you're taking. So going back so you can see what I mean here. We're going along the x-axis here. All right, when you do that, y is equal to 0. So what you're going to do is you're going to plug that in, and you're going to look and see what the value of f of x comma 0 is. Well, if you do that, you end up just getting x squared divided by x squared, which is equal to 1. Okay? So this is for all x not equal 0. So what we're seeing here is that the function f of xy goes to 1, all right, as x and y goes to 0 and 0 along the x-axis. All right, but now let's flip this. Let's talk about as we go from the y-axis. Okay, so when you're going along the y-axis, you're putting x is equal to 0. When you plug x is equal to 0 in, this is what you get. Minus y squared divided by y squared. And that always equals negative 1. So what you're seeing here is now the function f of xy goes to negative 1 as x comma y goes to 0, 0 along the y-axis. So the limits along different paths here didn't go in the same direction. Okay, one was going to 1, one was going to negative 1. So this limit does not exist. All right, so since f has two different limits along two different lines, the given limit does not exist. Okay, and this confirms what we saw from the numerical tables that we were putting together. All right, so now let's look at limits that do exist. Just as for functions of one variable, the calculation of limits for a function of two variables can be greatly simplified by using the property of limits. All right, the limit laws can be extended to functions of two variables. So the limit of a sum is the sum of the limits of a product is the product of the limits, and so on and so on. So in particular, the following equations are true, and the squeeze theorem holds. So if you take the limit of x, y of just x, well, that's just equal to whatever the a value. Limit of x, y of just y, that's just equal to the b value. And the limit of a constant is just still a constant. All right, I just want to talk real briefly about continuity now to end this section. Okay, so we know that evaluating limits of continuous functions of a single variable is easy. It can be accomplished by direct substitution. All right, continuous functions of two variables are also defined by direct substitution property. So if a function f of two variables is called continuous at the point a, b, if you can evaluate the limit by just plugging in the values a, b. All right, so we say f is continuous on D if f is continuous at every point a, b in that D, that domain. So for some of these problems that you're going to do this week, what you're just going to do to evaluate the limit is just plug it in. And if you want to evaluate limits, you can use all the properties and all the tricks you've learned to evaluate limits from previous calculus courses.